Good morning, Honorable. In this class, we are going to talk of the introduction to mass transfer. Um, that's introduction to mass transfer. First, we'll like to deal with the diffusion mass transfer. Just seen this. Look at this diagram. When salt particles are added into the cup of water. So, being high density of the salt particles, always settle down at the bottom of this cup. When the water is added, when the time goes on, what happens? The salt molecules is slowly getting diffused into that water. So, such a way that the mass diffusion, that is mass transfer, takes place from high concentration side to lower concentration side. Similarly, we can experience the same um, example for that when that sugar is added into the milk. So, being high density of that sugar molecules, it will be deposited initially at the bottom, and after that, what happened? The water, the sugar molecules is slowly getting diffused into the water. Yes. Such a way that the mass transfer takes place. This process is called a diffusion process. So the diffusion process always takes place from higher concentration side to lower concentration side till it reaches the equilibrium. That is very important. As such, as we have seen in that heat transfer, the heat flows from body at high temperature to body at low temperature. As long as the temperature difference between two bodies, the heat transfer takes place, and the heat transfer stops when it reaches the equilibrium. The same phenomenon. It's followed here that as long as that concentration difference exists, the mass diffusion takes place. When it reaches the equilibrium, it means that when that same concentration exists in all over the fluid, then automatically what happens? The mass diffusion stops. Here is a tank is separated by partition membrane. Here the left side tank is filled with the nitrogen, the right side tank is filled with the oxygen. Yeah, that is oxygen. Here the left side tank is concentration of nitrogen or more compared to the right hand side. Similarly, in that oxygen, the concentration of oxygen or more compared to nitrogen in the right hand side tank. So what happened here in this? That concentration, the diffusion takes place from higher concentration side to lower concentration side. So the nitrogen molecules is slowly getting diffused from left hand side to right hand side. Similarly, the oxygen molecules is slowly getting diffused from right hand side to left hand side till it reaches the equilibrium. So normally there are different kinds of diffusion process from solid to solid, solid to liquid, liquid to gas, and gas to gas. And in this above examples, the diffusion rate is very high in case of gas to gas, because the molecular spacing between the molecules are very high, so that the diffusion rate is very high in case of gas to gas process. So, before getting into this mass transfer, you would like to know that basic concept. That is, these terms are very important. The mass density. The density is based on mass. We know that the density is equal to mass per volume. It is the ratio of mass to volume of the mixture. Molar concentration. The next one is molar concentration. It is the ratio of number of molecules which is present in the unit volume of mixture. That is C equal to M by V. Normally, it is designated by the symbol C. Then mass fraction, it is the ratio of density of the particular species to density of the total mixture. So it is called a mass fraction. It is normally denoted by the symbol m dot. The next one is molar fraction. It is the ratio between concentration of the particular species divided by concentration of the total mixture. That is x. Normally it is designated with the symbol x equal to Ca by C total. Now we are going to solve the problem. A vessel contains binary mixture of oxygen and nitrogen with a partial pressure of ratio 0.21 and 0.79 at 20 degrees centigrade. If the total pressure of the mixture is 1.1 bar, calculate the following: mass density, molar density, mass fraction, and the molar fraction. As we know that PV equal to MRT. From this we can calculate P equal to M by V RT. So M equal to Nm, number of moles into molecular weight. You know that. So we say that we substitute this one, then finally we arrive as P is equal to C by Gt. M into R, that is R is gas constant, that is gas constant. G is nothing but universal gas constant. So C is equal to P by Gt, that is the formula we arrived. And C is equal to N by V. M equal to capital N into M. So N is equal to M by M. So C is equal to, when we substitute this one formula here, then M by V is nothing but rho. So ultimately we arrive this rho equal to Cm. So we do remember these two formulas, C is equal to P by Gt and rho equal to C by Cm. That we have to remember these two formulas, where G equal to universal gas constant, that value is 8314.13 joule per kg mole Kelvin. So in this formula, P, that is 0.21 into partial pressure, 0.21 ratio into what is the total pressure, 1.1 into 10 power 5. So it comes around 23,100 Newton per meter square, that is Pascal. P of nitrogen 0.79 into 1.1 into 10 power 5 equal to 86,900 Newton per meter square. So C is equal to P by GT. C is equal to P by GT. So, C equal to 0.231 into 10 power 5, 8314 into 293. So 9.483 into 10 power minus 3 kg mole per meter cube. Then C of nitrogen equal to P by GT. That comes around 35.673 into 10 power minus 3 kg mole per meter cube. Now rho equal to Cm. So 35.673 into 10 power 3. What is the molecular weight of nitrogen is 28, and it comes around 0.9988 kg per meter cube. So mass fraction of oxygen equal to density of oxygen divided by density of total mixture. We know that density of oxygen and the density of nitrogen, when we sum of this one, will be getting this answer 0.233. And mass of nitrogen, rho of N2 divided by rho, is equal to 0.767. Then molar fraction X of oxygen equal to C of oxygen divided by C total, and comes around 0.21. Then molar fraction of nitrogen, C of nitrogen divided by C total, 0.79, comes around 0.79. So from this we can clearly identify that the molar fraction of oxygen, that is 0.21, and the molar fraction of nitrogen equal to 0.79. Normally that we can check this value with that. Normally the nitrogen, it is 79% of nitrogen. I mean, by volume it exists in the air. 21% of oxygen by volume that is available in the atmospheric air. Such way that we can cross-check these values. Next, one-dimensional steady-state mass diffusion through plane membrane. Here, it's the left-hand side. The high concentration side exists. Right-hand side, lower concentration of molecule exists. At x is equal to 0, C is equal to Ca1. X is equal to L, C is equal to Ca2. And the thickness of the membrane, it is denoted by the symbol L. Now the mass transfer takes place from higher concentration side to lower concentration side. So the general equation is dou squared C by dou x squared plus dou squared C by dou y squared plus dou squared D by dou z squared, or d by d equal to 1 by d dou c by dou t. Similarly, the same formula that have been used in the heat transfer. Used in this equation. Since it is a one-dimensional mass diffusion equation, the mass transfer takes place only in x direction. and no chemical reactions, that is R equal to 0. So when this term gets knocked off, then dou squared C by dou Q square equal to 0. While integrating this one, dou C by dou X equal to C1. Then C is equal to C1x plus C2. So we have two integral constants. In order to solve these two integral constants, we need two boundary conditions. So at x is equal to 0, C is equal to CA1. When you substitute this value, C2 equal to CA1, we'll be getting that value of integral constant C2 equal to CA1. Put CA1 value in equation 1. Then finally C is equal to C1x plus CA1. At x is equal to L, C is equal to CA2. When you substitute this one, CA2, C1 of L plus CA1, then finally C1 integral constant CA2 minus CA1 divided by L. When you substitute this value in this equation 1, we'll be getting this equation C is equal to CA2 minus CA1 divided by L plus x into x plus CA1. According to fixed law of diffusion, m dot equal to minus dA dou rho by dou x. That is, mass flow rate is directly proportional to density gradients and area of membrane. And that is, we can say in other words, the mass flow rate is directly proportional to density difference and it is inversely proportional to thickness of the membrane. Similarly, what we have seen in the heat transfer. Heat transfer, the amount of heat is directly proportional to temperature gradient. Here, the amount of mass transfer is directly proportional to density gradient. That is the same phenomenon here in this. And in heat transfer, heat transfer is directly proportional to inversely proportional to thickness of the membrane, thickness of the wall, whereas in the mass transfer, the same phenomenon, mass flow rate is inversely proportional to thickness of the membrane. So molar flow rate, when we express in terms of m dot equal to minus dA dou C by dou X. So dou C by dou X equal to CA2 minus CA1 by divided by L. So m dot equal to minus dA CA2 minus CA1 by L. Then we can arrive this del C equal to L by dA. That is, L by dA is called the diffusion resistance. Similarly, this diffusion resistance is going to be varied with respect to geometries. For a cylinder, ln R2 by R1 divided by 2 pi LD. For sphere, R2 minus R1, 4 pi R1 RT D. The same here. This in heat transfer, ln R2 by R1 divided by 2 pi LK. Is the K is the thermal conductivity in heat transfer, but here in this mass transfer, the D, diffusion coefficient, is the factor for this. So we have to replace that K and substitute D for the mass transfer problems. Hydrogen gas, look at this problem. Hydrogen gas at 3 bar, 1 bar, 1 bar are separated by a plastic membrane having thickness of 0.25 mm. The binary diffusion coefficient of hydrogen is 9.1 into 10 power minus 8 meters per second. The solubility of hydrogen in the membrane is 2.1 into 10 power minus 3 kg mole per meter cube bar. Uniform temperature condition is 20 degrees centigrade. Find molar concentration on both sides, molar and mass flux of hydrogen. Here the diffusion coefficient D equal to 9.1 into 10 power minus 8 meters per second. Solubility equal to 2.1 into 10 power minus 3 kg mole per meter cube bar. The solubility is nothing but the amount of molar concentration present in the unit bar. So we have to find out that the concentration C is equal to solubility into pressure. What is the pressure here? The pressure here is 3 bar at the left hand side. So 2.1 into 10 power minus 3 into 3, it's equal to 6.3 into 10 power minus 3 kg mole per meter cube. So Ca2, 2.1 into 10 power minus 3, that is right hand side, and it comes around 2.1 into kg mole per meter cube. So everything is converted into kg mole per meter cube. That is called the molar concentration. Now the molar flux equal to Na by A d Ca1 minus Ca2 divided by L. That is what we have seen, because it's a plane membrane. So that formula is here. If it is in case of cylinder, we have to substitute ln R2 by